Okay, we're going to do several lectures or several videos on neural networks, and this comes from a book um, called Discovering Knowledge in Data: An Introduction to Data Mining by Daniel LaRose, and I highly recommend this book. And this is Chapter 7 on neural networks, and we will cover in these videos at least up to here, at least those parts. Okay, now I think there are some videos called Introduction to Data Mining 1 and 2 or something like that on my site, and so in there, if you remember, we had some pictures like this, and if you recall, this is the task of classification. So what does that mean? That means you have some data that is called labeled data, or has a class variable, or a target variable, or an output variable. So for example, I gave an example here where you might have each dot here represents an individual, or I'm sorry, a couple, and we might know the x and y coordinates of each point here, and the x coordinate might be the husband's salary in the couple, and the y coordinate might be the wife's salary in the couple. And then you might want to predict whether they own their own house, given the wife and husband's salaries. What's that? I don't know what that was. And then, so you might want to try and predict whether they own a house or not. Now, this data, maybe the blue represents that they own a house, and the green represents that they don't own a house. So what we're saying is that we have, however many couples here, maybe there's 25 couples here, or 25 dots here, where we know the target variable, or in other words, we know whether these people own houses or not, because we can see they're either blue or they're green. They either do own a house or they don't. So we have data where we have the target variable the value of the target variable is known. So it's called labeled data. Okay. Now suppose we got a new piece of data, a new couple that was unlabeled. Could we build a model from our labeled data, which is called our training data? Could we build a model from our training data or our labeled data, so that once we have the model, we can now make a prediction for some new unlabeled couple. Some new couple, we only have their wife and husband salaries, but we don't know whether they own a house. So that's the task here. And so the model, for example, could be just a linear model, and we talked about that, where you get just a line like this, and if it's above the line you might say it's blue, and if it's below the line you might say it's green. Okay, now that's not a very sophisticated model. And then we have more sophisticated models like decision trees, which will give you something like this. Okay, and then we also said that you can build what are called neural networks, and they are even more flexible than decision trees, because their classes can be kind of curved. The boundaries of the classes can be curved, so that's more flexible. So anyway, that's the kind of thing we're doing here. So we want to build a model. So this might be a model. So anything up here, if we had a new white dot which is up here, we'd say, oh, they are part of the they own a house, and if it's down here, we'd say they don't own a house. Okay, now let's go back to here. And let's look at another kind of example. Why doesn't that work? Not working. I'll pause here. So here's another kind of example. This is a picture of a neural network. Also, this is kind of a more standard picture. And here what you have is you have a bunch of nodes here, and we call this set of nodes the input layer. We call this set of nodes the output layer, and we call this the hidden layer. Okay, and we're doing the same kind of thing that I was just talking about before. We have some pre-labeled data, and the variables here, we have more than just two variables. In that last picture, we had just just two variables. But here we have many variables. For example, we have age, we have education, which is numerical. We have race, which normally we think of race as one variable that can have several different possible values, like white, black, Asian, and so on. But here we've split it into many variables. So we have race. White is one variable, and it's going to be a 0, 1 variable. And so in other words, if it's 0, it means not white. If it's 1, it means white. And here we also have race black, which is also a 0, 1 variable. So if it's 0, it's not black, and if it's 1, it is black, and so on. So we've taken a categorical variable and we've made it into 0, 1 variables. 0, 1 variables are also categorical, but here, next one normally we'd say sex can be male or female, but we've broken this up into two separate variables: sex male, 0, 1 variable; sex female, 0, 1 variable. We have capital gain, capital loss. I guess it's the same kind of thing. Hours per week working, that's a numerical variable. And then work classification, so are you a government worker, and so on. These are also 0, 1 variables. And also marital status, they've changed these also to 0, 1 variables. Okay, so anyway, you have, so you might have, say, 100 people, or 1,000 people, or 10,000 people. In the last example with those dots and the couples, I said we had, say, 25 labeled examples. So here we might have, some number of labeled examples. Let's say we had 10,000 labeled examples. It means 10,000 people where we knew their age, education, race, gender, capital gains, working class, marital status. And we also, since I'm saying they're labeled examples or labeled cases, we also know whether or not they earn less than or more than $50,000. So what we're trying to do, in the last example we were trying to predict whether they own a house or not. In this example we're trying to predict whether they earn $50,000 or more or not. So we have, say, 10,000 cases that are labeled where we actually know whether those people do earn more than $50,000 or not. And then the object is still the same. If we take a new case, a new person, where we know this data, but we don't know this. We don't know whether they earn 50,000 or more. Can we build a model from the 10,000 labeled cases so that we can make a prediction about this new person as to whether they earn more than $50,000 or not? Okay, so this is the kind of task that we want to do. This is and we want to use what's called a neural network to make this model. Okay, so let's go to the beginning here. The inspiration for neural networks was the recognition that complex learning systems in animal brains consisted of mostly interconnected sets of neurons. So animals and humans have very complex learning systems, and they observe these and they see that they consist of interconnected sets of neurons. Although a particular neuron may be relatively simple in structure, dense networks of interconnected neurons could perform complex learning tasks such as classification and pattern recognition. That's what humans can do, and animals. The human brain, for example, contains approximately 10 to the 11th neurons, each connected on average to 10,000 other neurons, making a total of that many synaptic connections. Artificial neural networks, here after neural networks, represent an attempt at a very basic level to imitate the type of nonlinear learning that occurs in the networks of neurons found in nature. Okay, the reason they call it nonlinear, maybe we'll discuss that later. For now, don't worry about that. As shown in figure 7.1, a real neuron uses dendrites. Let's see. So here's this is supposedly a drawing of a real neuron, and this is what we mean by an artificial one. Uses dendrites to gather inputs from other neurons. So it gets inputs on this side, and then depending on the strength of the inputs here, it might fire over here out and give inputs to other neurons. And combines the input information, generating a nonlinear response. So it doesn't have to be a linear firing. That means, like, if it's low, if it fires a little. If it's high, it fires a lot. It doesn't have to be like that. It could be, if it's low, it doesn't fire at all, and if it's high, it fires. Or that's just like that. So that would be nonlinear. Which it sends to other neurons using the axon. The axon. That's the axon. There. Okay, figure 7.1 also shows an artificial neuron model used in most neural networks. So this is an artificial one. This is what we just saw in the last picture before. Here you have the input variables, and then the hidden layer is here, and then you make a prediction over here at the output layer. Okay, so the inputs x sub I are collected from upstream neurons or the data set, usually just from the data set, and combined through a combination function such as this. So we can take all the inputs and we do something with them, like maybe we add them up or something, which would mean summation, which is then input into a usually nonlinear activation function. So this is supposed to be some nonlinear activation function to produce an output response y, which is then channeled downstream. So we sum them up, and then we do something to it, and then we make our prediction, or we output something. What types of problems are appropriate for neural networks? One of the advantages of using neural networks is that they are quite robust with respect to noisy data. Because the network contains many nodes, artificial neurons, with weights assigned to each connection, the network can learn to work around these uninformative or even erroneous examples in the data set. However, unlike decision trees, which you should have learned about, or I'll have another video about decision trees, which produce intuitive rules that are understandable to non-specialists, neural networks are relatively opaque. Well, anyway, so that just means we don't really know how they work. We just can get the results from them. We can put in an input and get an output, get a prediction, but we don't see the inside of it particularly. Okay, now they talk about input and output encoding. So, like you saw at in that picture I showed you a little while ago, we changed some of the variables. For example, gender, which is usually male, female, we changed it to 2 variables, one for male and one for female. So how do we have to change our variables in order to get them to work properly in a neural network? So numeric variables, what do you do with them? And non-numeric, like gender, like the other example was race, marital status. How do we handle those? How do we handle all different kinds of variables when we want to input into the neural network? One possible drawback of neural networks is that all attribute values must be encoded in a standardized manner, taking values between 0 and 1. Now, for example, in Weka, it does this for you, so you actually don't have to do it. But formally, a neural network needs to have that. But since Weka sort of handles that as a separate step, but handles it for you, you don't even need to do it. But anyway, even for categorical variables, they have to be between 0 and 1. Later, when we examine the details of the backpropagation algorithm, we shall understand why this is necessary. For now, however, how does one go about standardizing all the attribute values, so all the input variables? For continuous variables, that is numeric variables, this is not a problem. As we discussed in Chapter 2, we may simply apply the min-max normalization. So you take a value like somebody's age, and then you subtract the minimum age for the entire data set, and then you divide by the range of the ages. So let's see, do they give an example here? No. So for example, let's say someone is 50 years old, and the minimum age in the data set is 10, and the range is, say, from 10 to 70. So that means a range of 60, 10 to 70, 60. So what did I say? 50 minus the minimum I said was 10. So 50 minus 10 is 40 divided by, I said, 10 to 70, so 60. So 40 divided by 60. Okay, so 2/3, right? So that's the value. It would be 0.6666666, right? So that's what we'd say. Somebody who was 50 years old would be encoded as 0.6666. Okay? So that's called the min-max normalization. This works well as long as the minimum and maximum values are known and all potential new data are bounded by them, between them. So if we have minimum and maximum, do we really know that the new data will be between there? Not really so sure about that, but anyway, neural networks are somewhat robust to minor violations of these boundaries. So if more serious violations are expected, certain ad hoc solutions may be adopted, such as rejecting values that are outside the boundaries or assigning such values to either the minimum or maximum value. Categorical variables are more problematic, as might be expected. If the number of possible categories is not too large, one may use indicator or flag variables. That's what I called 0-1 variables. He calls them indicator variables or flag variables. For example, many data sets contain a gender attribute. So if you collect data on people, one thing you may find out about is the gender of each person. Right? It's a typical thing that you would check for. So containing values male and female and unknown. Since the neural network could not handle these attributes in their present form, we would instead create indicator variables for female and male, or 0-1 variables. Each record would contain values for each of these two indicator variables. Records for female would have a value of 1 for female and 0 for male, while records for males would have a value of 0 for female and 1 for male. Records for persons of unknown gender would be 0 and 0. In general, categorical variables with k classes may be translated into k-1 indicator variables. So here we have gender, which has three possible classes in the sense that it could be male, female, or unknown. So we translate that into 3 minus 1, k minus 1, 3 minus 1 indicator variables. So we translate it into a male indicator variable and a female indicator variable, and that's enough. That will cover all possible cases, right? As they explained up here. As long as the definition of the indicators is clearly defined. Be wary of recoding unordered categorical variables into a single variable with a range between 0 and 1. So, like you might say race, or let's see, they have marital status. For example, suppose that the data set contains information on marital status. Suppose we code the attribute. Now this is not the way we did it in that last picture, but suppose that we code the attribute values divorced, married. For example, suppose that the data set contains information on marital status attribute. Suppose that we code the attribute values divorced, married, separated, single, widowed, and unknown. So we have a categorical variable called marital status. And these are the answers to what that could be. Divorced, married, separated, single, widowed, and unknown. These are the values it can take. Now we know that we need to recode to between 0 and 1. Suppose we tried it this way. We said divorced will be 0, married will be 0.2, this will be 0.4, this will be 0.6, and the unknown will be widowed will be 0.8, and unknown will be 1. Okay, that seems like we tackled the problem. But there's a problem in doing this, and that is that these numbers have an implied order in them, right? Right. But these don't have. There's no such implied order here, but we've given it an implied order by encoding it in this way. Then this encoding implies, for example, that divorced is closer to married than it is to separated, and so on. Okay? The neural network would be aware only of the numerical values of the marital status field, not of their pre-encoded meanings, and would thus be naive of their true meaning. Spurious and meaningless findings may result. With respect to output, so you shouldn't do it that way. Okay, instead you could make several 0, 1 variables like they did and like I showed you earlier. With respect to output, we shall see that the neural network output nodes always return a continuous value between 0 and 1. So the output is always going to be between 0 and 1. So how do you interpret that? For example, in the problem where we were trying to predict income, we're going to get a value between 0 and 1. That doesn't really tell us income, right? How do we use such continuous output for classification? Many classification problems have a dichotomous result, an up or down decision. So that was the example that we saw. Either the person earns more or less than $50,000. For example, here's another example. Is this customer about to leave our company's service or not? So that's dichotomous. For dichotomous classification problems, one option is to use a single output node, such as figure 7.2 here. So this is an example, and with a threshold value set a priori which would separate the classes, such as leave or stay. For example, the threshold of leave if the output is greater than 0.67, and an output of 7.2 from the output node would classify that record as likely to leave the company's service. So if you have so you could have this kind of threshold value, and that would handle this situation. Single output nodes may also be used when the classes are clearly ordered. For example, suppose that we would like to classify elementary school reading prowess based on a certain set of student attributes. So we're trying to classify or predict how good a student's reading is. Then we may be able to define the thresholds as follows. So we could have, if they have a first grade reading level, the output is between 0 and 0.25. And if they have a second grade reading level, the output will be between 0.25 and 0.50, and so on. Fine-tuning of the thresholds may be required, tempered by experience and the judgment of domain experts. Not all classification problems, however, are soluble using a single output node. For example, suppose that we had several unordered categories in our target variable, as for example with the marital status above. So suppose we're trying to predict marital status, and in this case we would adopt for a 1 of n output encoding, where one output node is used for each possible category of the target variable. So in this case you'd want to have more than one output node. For example, if marital status was our target variable, that is what we're trying to predict, the network would have 6 output nodes. Okay? Because what do we have? 1, 2, 3, 4, 5, 6. One for each of the 6 classes. The output node for the highest value, the output node with the highest value is then chosen as the classification for that particular record. So each of these are going to be output nodes, and so they're each going to get some value assigned to them by the model once you have an input. But then you choose the one that has the highest value as the actual predictions. Okay? One benefit of using 1 of n output encoding is that it provides a measure of confidence in the classification. So if this one is assigned 0.6 and all the others are less than 0.6, you sort of have some measure of confidence in how good this is. For example, if this is 0.6 and all the others are 0.1, then this is sort of gets a much higher, maybe we'd say it's more probable. Okay, in the form of the difference between the highest value output node and the second highest value output node. Classifications with low confidence, small difference in node output values, can be flagged for further classification. Okay.